And hello, welcome. Last video we talked about some other signals we can use for testing. We talked about using square waves before, square wave signals, and some binary signals. Okay, so we saw that binary signals are pretty good approximation of square wave if you don't mind all the other noise, as you can see here. Yeah. That's what I was trying to bring across. Okay, the square wave and the binary signals, they're pretty good. Okay, so the binary will be, I think, in column. Yeah, I don't know where it is. Oh, this is just a binary sequence. So square wave versus binary. Okay, so yeah, this is the sine. Oh, I think this is a sine wave. This is not a square wave. Oops, I kind of mixed it up the last time. So yeah, it's a sine wave versus the binary signal. Okay, so point is in the last video, when we have this sine wave and we compare it with the binary sequence, okay, it's actually pretty good. It's a very good match, okay, between the binary and the sine wave. Yeah, sine wave being, of course, the cleanest of all signals. Binary signals, they have the main frequencies of interest which you want to test. Now I have 5 frequencies which I can test for within one test at the same time. Yeah, and this will have relatively high signal to noise ratio at that point. Okay, because there will always be some background noise and fluctuation at your frequencies of interest. So you want to make sure for the frequencies you're testing, your test signal is much stronger than the background noise. And for sine waves, that definitely is the best. But if you can't use sine waves, I think, yeah, as we can see from the results here, the Fourier transforms, the strongest signals here are, and they're way above background noise. The strongest signals are your signals of interest. So binary approximation of sine waves or square waves, in this case binary approximation of square waves actually does pretty well. Okay, because you have all of these other peaks as well, which you may or may not want them. Okay, so now next, actually, I want to carry on. What if you want to test for more than these frequencies, right? If you want more than 5 frequencies, you want 10 frequencies at once or 30 frequencies at once, okay, you can actually keep adding the number of sine waves that you actually test, or you make the multi sine wave frequency, then you kind of take a look at your binary frequency. Of course, that will take a bit of programming. So well, what other kind of signals can we use? Okay, so the answer is that we can use noise signals. Okay, noise signals. Why use noise signals? Okay, because in the if you want equal frequencies, equal amplitude at all frequencies, you would use noise. So a noise input will be good if you want many to test all the possible frequencies at one go. Okay, so let me show you how the noise is being done. Okay, noise is being done here. Okay, I mean, you can take a look at this input generator. Okay, oh, this thing is still running for some reason. Alright, this is a sine wave input. Okay, great. Right, I think I should stop. Yeah, I can stop this. And basically, yeah, the way you can do noise is just change this signal type. Instead of going with a sine wave, you can actually change it to random. Then you will have this noise signal. Okay, and then basically you can run a Fourier transform on the noise signal, and you'll find that yeah, this is a noise signal going between 14 and 16. Okay, and doesn't matter what the frequency is here, because noise is noise. You can do it at 0.0001 hertz. It will still be like a noise signal. Okay, so changing the oscillation frequency into this VI doesn't really matter, but changing the amplitude and the offset, that's what will matter. So if I change the amplitude to 4, then the noise signal will oscillate with a value of 4. And if I change the offset, let's say to 16, then it will change accordingly. Okay, so it's a bit harder to see, so let me change this back to 1. I'll change this to 17. So you can see you can change the place where this thing oscillates. Just put it back 15. So you can see you can change it as and how you want. Okay, so that's how the noise you can generate noise using this signal generator. Okay, and it doesn't really matter whether you add them together or subtract them. Noise is noise. Okay, noise is noise. So okay, so one thing is that we can actually look at some noise signals. We can look at the frequency response, the frequency representation of that, and of course we can also approximate the noise with binary. We can approximate noise with a binary signal using the method we were talking about before, using this absolute thing. Okay, so this is noise and binary noise. Okay, again, I think over here I did not actually solve the what do you call that? I have not solved the divide by zero problem yet, so let me just solve it now. But I'll just tell you how the VI works. Okay, you can just input in this frequency in here, which I think doesn't really make sense at all, because you don't really have to decide any frequency. So yeah, I think I'll just delete this. This doesn't make sense at all. The only thing you need to decide here are the offset and amplitude, because no matter how you change the frequency of this VI, it doesn't really make a difference. At least just by inspection you cannot tell the difference. Okay, so let me again solve the divide by zero problem by putting in a case structure. Now use the comparison tool, equal to 0. Okay, if this is equal to 0, I need to output a 1. So let's put a constant of 1. If this is equal to 0 and this is not equal to 0, then I'll just wire the input through. Oopsie. Let me Control Z that. Draw this terminal to this terminal, and this is what I will delete. Okay, now I'll bring this whole case structure up here just to deal with the 0 divide by 0 problem. Oopsie. Clean up wire. Okay. Now, yeah, this thing should about work. So I'm using the same thing. I divide by, to convert this noise signal into a binary signal, I'm using the same thing. Okay, and once I'm done, what I do is I use this VI to write the output. Okay, I've not mentioned how this thing actually works yet, if I'm not wrong, at least for this video. But just a reminder, or maybe I don't know. Yeah, well, how I write the output to a CSV file, or those LabView files, LabView measurement files, LVM files, is with the use of, okay, all the files are here, all the .lvm files, they're over here. Okay, the way to do it is to use file IO, go to write measurement file, and then there'll be this dialog box. The action will be to save to one file. I usually like to overwrite the file if the file name already exists. File format will be LVM text. I'll use no headers for segment headers. And for time column, I will use one column only. Delimiter, I will use comma. So after that, you can just wire in your signals and where you can choose where you want to save this output file over here in the file name. Okay, so that's just a very brief introduction into this this write VI, and the only thing you need to give it, very simple, is just a time varying double output. Then it will start to write all the signals that you want. Okay, I don't usually like to give it arrays. I usually like to give it just one signal over here. All right, I give it one constant, double numeric constant that is time varying. Okay, which means it's just a number with some decimal places, a real number with some decimal places, and it will fluctuate up and down with time. So that's what you will have with this signal writing to measurement file VI here. Okay, so I'll cancel this and I'll clean this up. I'll remove loose ends. Okay, so this is the noise and binary noise, and the thing will be like this. As you can see here, the graph was running, the simulation was running before. It was going with this sort of oscillations, Okay, and I think there's a little bit of something a little bit off. My amplitude, I didn't kind of I have a noise signal. Okay, the noise signal will be the absolute value will be taken here. Then you kind of divide it, then you multiply by the amplitude. Okay, you multiply by the amplitude. Okay, so that will help you with the binary noise part. I think I forgot to multiply by the amplitude for the non-binary noise, so I need to delete this wire branch, and I'll need to multiply here as well. So this is the amplitude, and this will be added here, and this will go here. Okay, so this is how my noise and binary noise block diagram will look. Now, before I start running, I'm going to at least give you some insight. Okay, so this is the binary noise signal. Okay, the noise signal is kind of a little bit off because I forgot to actually, what do you call that? I forgot to set the amplitude right, so it's actually an amplitude of 1. Alright, so that's not exactly correct, but okay, we can actually just analyze the data anyhow. Okay, so let's open this up. Okay, see how much time I have remaining. We'll just open this up with LibreOffice Calc. Okay, I'm going to save it as a CSV, binary noise signal.csv. Okay, and I'll change it to versus noise signal. Okay, so this is a binary noise signal .csv, and I will have a noise signal here, which I can also open using LibreOffice Calc. Okay, I'll copy all of this and I will just put it over here. Insert columns before, and here's where Okay, so this is noise signal that goes over 1000 seconds. Okay, so yes, this is where it is. I'm going to use a text CSV format to save. Then I will just port it into MATLAB. So this is noise versus binary noise signal. Okay, now with MATLAB, okay, noise versus binary noise. Let's take a look at the frequency response, or the frequency domain. Okay, remember the first column is actually just noise, the second column is binary noise. Okay, of course, so you can see one signal is higher amplitude than the other, of course, because I forgot the I forgot to actually deal with, you know, the noise, not the noise part. I forgot to deal with changing the amplitude to make it right, as I did just now earlier in the video. Okay, now we take a look at both of these. We can see that the input signals are basically a mixture of frequencies all over the spectrum, and you can see it's a very even, a nice even sort of spread of frequencies. Now, if that's what you want to use to test your signals and get a frequency response, by all means, it is a very nice signal if your system is linear time invariant. And as long as your signal is much greater than the background noise, I think you should not have a problem. However, if you have certain non-linearities, this won't be a very clean signal, because yes, you're testing everything at one go. But some what do you call that? Some frequencies may have certain non-linearities. Maybe, I don't know. There are some frequencies that you might not want to test your system at. You want to test it at certain particular frequencies. Then what you do is, you can't use the whole frequency band here. You cannot use every single frequency. Maybe you're only interested in the frequencies over here, the lower range frequencies. All the frequencies below 1 Hz. The higher frequencies you don't really care that much about. Okay, how then do you like cut off all the higher frequencies, so to speak? Okay, one of the ways is with this thing called a filter. Okay, so at least just now just now the demonstration shows you what the noise looks like in the Fourier transform, fast Fourier transform. Okay, if you don't want all the noise, you might want to use a filter. Okay, so I can cut off all the higher frequency signals and just go for the lower frequency signals. Okay, so how do we do that? Okay, one of the ways is to just use this transfer function. Okay, it's a linear system. Okay, I'll just use a transfer function, and if the transfer function is 1 over s plus 1, we will have this thing called low pass filter. Low pass filter. Continue loading. So I'm just going to have a low pass filter here. Low pass means to say I'm only taking the lower frequencies. I have this thing called low pass filter. So if you take a look at this MATLAB, okay, if you take a look at this MATLAB and you say, okay, I don't want to deal with the higher frequencies. I only need to deal with the low frequencies. Okay, I only want to deal with the lower frequencies. What do? I can insert a low pass filter, and most of the higher frequencies will be filtered out. Means to say that you won't see them in this Fourier transform diagram. So, okay, so we'll try the low pass filter. I will try to write it for a while, and we'll see what happens. Okay. So let's see. We will. Okay, so this is a binary noise signal, which I don't want to mess around with, and we can see the binary noise and noise are pretty much the same. So binary noise means to say I will alter my signal between 2 values only, and noise is just noise. Okay, so let's try the low pass filter. We'll do it for a while. Okay, let me have a new VI. I can demonstrate how this input-output file thing actually works. Okay, so I'm going to put this here, the low-pass filter. Okay, it's lagging a little bit, but should be able to load it very quickly, shortly. Okay, so anyway, I will pass this noise into the low-pass filter. Okay, pass it into the low pass filter, which is just a transfer function 1 over s plus 1. Okay, yeah, again the idea is that the system will be will have some lag in response. Remember for step response of this first order transfer function, for step response, if your input's like this, and then your transfer function will take some time to get up here. So you can see that there's some sort of lag, right? Yeah, there's some sort of lag. Okay, why is this lag? Why is this lag here? Because all your higher frequencies, I mean your your output cannot respond fast enough because the higher frequencies are so-called filtered out by the transfer function. So that's why they call it a low pass filter. Yeah. Okay, so yeah, oh man. Okay, so let's continue. Yeah, let's see what the low pass filter signal looks like. So I'm going to have it write to a measurement file, and that will be in file IO. Write to measurement file. Okay, let's call this file in the desktop. Okay, we'll call it filtered white noise. And don't ask me why it's called white noise, but white noise is the other term that's used to describe noise. Okay, no headers, use one column only, delimiter, comma, save to one file, overwrite file. I want to save it on the desktop with a filtered white noise. Of course, if you have a different account, you just change the file name and location where you save it. Okay, so this is the signal, and just for your reference, we can actually pass it on into the waveform chart. Then you can see what the noise looks like. Filtered noise. Okay, so we'll have a lot of signals in that one waveform chart. So is this noise and binary noise waveform chart? Okay, so I'll put noise, filtered noise, and binary noise because that's what it's actually showing. Okay, so let's see what this will do to the spectrum. Okay, so let's press play. Can you see the green is your new plot? Okay, the green part is the new plot, and it's really a low pass filter. Okay, so you can see the amplitude of oscillation is a lot less. Now it's a bit hard to see, and you can see the green one, the green parts of the graph are sort of hard. It's very hard to see. Okay, fair enough, but okay. Yeah. But okay, if you can see what you're seeing on this graph is that you have your binary signal, which is the blue colored one, just the white noise, which is the red colored one, and then the filtered signal is also oscillating, but not with the same frequencies. It's actually oscillating a lot less because the noise was filtered out. So the higher frequency noise is actually filtered out because of that lag time. Okay, so this is 60 seconds of white noise. Let's pass it through into the Fourier transform. Okay, so I will have binary noise, I will have noise, and I will have filtered white noise. I'm going to just delete all the rest of this because I don't really need it. Okay, so I will only want to have noise and filtered white noise to be my comparison. I will just open it up with LibreOffice. Okay, again, open it up. Open with LibreOffice Calc. This should only go for about 60 seconds, which it does. This filter white noise is also going to go for about 60 seconds. Let's open it here. Yeah, I need to open both. Okay, so let's do this. Let's put it here in the noise, and I will save it as filtered noise versus noise. I'll save it as a CSV. Okay, and what I'll need to do is, of course, I need to delete off some of the earlier bits of data, maybe up to 10 seconds. Okay, never mind. Let's insert the chart to make sure we are on the right track when we want to delete times, the initial transition time. Insert chart. After that we can do the Fourier transforms, and then you'll be more or less done. Okay, so you see, things kind of settle down after maybe 20 seconds. Okay, so maybe we'll just delete up to 20 seconds. Okay, and voila. Now just delete the rows. Now just delete this chart because that's not going to matter. So we can run a Fourier transform on this, and we'll see what the noise is like. Okay, so this will be here, filtered noise versus noise. Okay, and there's a lot of MATLAB files here. Okay, and let's take a look at the plotted figures, there's just too many plotted figures there. All right, now let's again take a look and can show you what the filter does. Okay, so the blue signal is of course noise, because we know noise signals have a sort of constant frequency across every single frequency. But you can see the filtered white noise here actually will give a higher frequencies at it will be sort of more or less the same at lower frequencies, but as you go to higher and higher frequencies, the amplitude just starts to drop off. Okay, it will start to drop off as you go into higher and higher frequencies. Of course, this Nyquist frequency is actually 5 Hz because we are sampling 10 samples per second. So that's 10 Hz. So 10 Hz divided by 2 is the Nyquist frequency, 5 Hz. So you can see what this low pass filter actually does. So this is one way of generating an input where you want to focus on a few frequencies. Okay, a few frequencies. Okay, so you can use this low pass filter and of course increase the number of you can increase your amplitude here, so that the lower frequency signals can be sort of simulated properly. Now that's all well and good, provided that your controller can actually vary the input like that. Okay, if your controller cannot vary the input up and down like white noise, then you're gonna have a problem. I mean, how are you going to test the so-called test everything? You know, if your controller is like slow in response, then you cannot have a white noise signal as a test input, as an input to do a broadband frequency response test. Meaning to say, if your controller cannot move, like that, chances are this method may not work very well, because you have to move up your so-called, for example, for this maybe it can be a filter, the fuel input up and down like crazy. Okay, in real life that may not work. So what's one way of dealing with this? Okay, one way is to use if you take a look at the binary noise signal, maybe you want to lengthen the binary noise signal. Okay, maybe you want to lengthen the binary noise signal. So instead of it going up and down very, very quickly, you might have it go up and down like this. One, down, one, and down. Okay, so maybe instead of these oscillations happening maybe 1 second, 2 seconds, or maybe 0.1 second, right? 0.1 second. Maybe you want this to hold here for maybe 5 to 10 seconds, yeah? Or maybe 2 to 3 seconds even. I don't know. It really depends. Or 7 seconds. 7's a nice number. 7 seconds here. Okay. It will your machine will always wait 7 seconds before you have your next noise. So yeah, this is a noise signal. This is a noise signal. This is a noise signal, but it's a signal that it's a slow, sort of a slow noise signal. Slow noise. I like, because the oscillations are slower. Okay, so yeah, how then do you generate this thing? How then do you generate this slow noise signal? Okay, so this actually brings us into another kind of input, but I will discuss that more in the next video. Okay, so yeah, this is called pseudo random binary noise. Pseudo random binary signal. Okay, also called PRBS. So this has been used before to do testing of systems. So this is a very good signal because it also it has this advantage of testing multiple frequencies at once, just like the noise. Okay, it will test multiple frequencies at once. But the thing is, you don't you can actually account for this controller. The controller may be slow, so you might want to wait a while before changing, maybe 7 seconds or something like that. So this is what pseudo-random binary signals are about, and we can talk about that more in the next video. Okay.